this is first law of thermodynamics. So first law of thermodynamics is how energy in objects is transferred from one to another. This occurs when next, new, what's that word? Heat. I had that. There, heat. Heat particles exchange between objects to find how much heat is exchanged. You take the increase of heat and external work done by the system. Good. I'm going to do one change. Don't say particles. Just say heat exchange between objects. The reason is there are no heat particles. Okay? How energy in objects is transferred from one to another occurs when heat is exchanged between objects. To find how much heat is exchanged, you take the increase of external work done by this, or the increase in heat and the external work done by the system. There is an equation for this. I'm going to give it to you. We got room here? Yeah. Q equals delta U plus W. W is work. Q, let's see if anyone remembers. Q is? Heat. Heat, yep. And delta U, this one you haven't seen before. Delta means change. So delta U is change in U. U is internal energy. And look, Tori, you don't have to write it down. I wrote it down for you. I know, aren't I nice? In the practice you picked up today, if we get to it, we will talk about how to solve this equation. It is not difficult to solve. The one thing you have to be careful of is signs. You got to be careful with signs because all of these will have signs. Like you'll have positive and negative Q. You'll have positive and negative delta U. You'll have positive and negative work. So you have to be careful about what the signs mean, and that depends on what the problem says. So if the problem says it cools, that means your internal energy goes down because internal energy measures temperature. If it says work is done on a system, then it would be positive work. Okay, so you just have to be careful on the wording of the problem as far as the signs. But the math is obviously super easy. It's just adding and subtracting. Okay. All right, the next one is the clarifying one. So jump down to the third spot. Okay, so the next one is clarifying, not the question. So jump down to the third spot there. Okay, flow is essentially heat transfer, and however much is being transferred is how much is being lost. Okay, so when you're talking about heat transfer and you're talking about the flow of heat from one object to another, essentially how much heat is transferred is dependent upon how much the internal energy changes. There's also some work done sometimes. Think about conservation of energy. So when we did conservation of energy, we said Ke plus Pe initial equals Ke plus Pe final. Those were our energies, so they were equal to each other. But sometimes friction, that squirrely little devil friction, would act, and then we would add in the work that friction did. Same thing is here. So heat transfers into internal energy, but sometimes work is done. And when that work is done, you just add in that work to the problem. Okay. So for example, if I had 10 joules of heat and the internal energy changed by 12, then there has to be 2 joules of work that is done by the object, okay, in order to get those numbers to match. However. So however much heat. So whatever that value is. Okay, let's look at the questions here. All right, first one. Okay, what was the forerunner of the law of conservation of energy? So what did they have before that? It was something called caloric. Basically, they thought of it as this like invisible liquid that flowed from one object to another. And that's like that transferred, and as that transferred, it would take that energy from one thing to the other. But this is the key here: conservation of energy. The law is conservation of energy. This law here, thermodynamics first law, it is the conservation of energy. So, like, if I ask you to explain the first law of thermodynamics, and you said it's the conservation of energy for, conservation of thermal energy, I'd be like, yeah, that is what it is. Great. Okay? Doesn't have to be a complicated explanation. But the original idea was something called caloric. It does not exist. That's where energy came from, though. So we've realized this thing doesn't exist. So then we're like, okay, well, there has to be some transfer of something, and that something is energy. It's not something you can hold, it's not something you can touch, it's not something you can see, but it is something that changes from one place to another. All right, and essentially, simply, what is the first law of thermodynamics? It's how heat transfers. Very simply, it's just how heat transfers. Okay? And last one, why does temperature, why you raise your temperature when you rub objects together? You're turning mechanical heat into, or mechanical energy into heat energy. So the physical act of rubbing, that friction creates motion energy, and that turns into heat. Which then dissipates into the air and particles around it and becomes lost, quote unquote lost. It's not really lost, but the last group will talk about entropy, which is super interesting and super confusing to explain. So we'll see when we get there. Okay. And last one. All right, explain the diagram to me. Oh, pumping a tire. So, like, they're doing work, and that causes, like, transfer from one thing to another. Okay. So work is done on the pump. That will generate some heat. So the amount of work done corresponds to energy transferred. Good. Of the three laws, the first one's the easiest. Actually, they're really, none of them are that complicated. But the first law is just conservation of energy. Heat transferred equals the internal energy change plus work. So whatever your internal energy changes plus the work that you do, that's how much heat is generated, either into or out of the object. Again, that's why the direction matters a lot, because which way it transferred matters, whether it goes into an object or out of an object. Okay. Any of these things that you would like more of an explanation on?